Now let's talk about Le Chatelier's principle. It is the definition of it is if a stress is applied to a reaction mixture at equilibrium, so you're starting at equilibrium, a shift in the position of the equilibrium occurs in the direction that relieves the stress. So, starting at equilibrium, which way does the reaction have to go to establish a new equilibrium? And it predicts changes in the composition of an equilibrium mixture if a system at equilibrium is stressed or moved away from equilibrium. So starting at equilibrium, how does the reaction respond? And by respond, I mean, does it go in the forward direction, at which point it will shift towards products? Does it go in the reverse direction, in which case it will shift left towards reactants? So how does the reaction respond to reestablish, two E's there, reestablish equilibrium? And I guess one analogy, so I'm sitting very peacefully and all of a sudden the dog jumps on me and disturbs my equilibrium. And then to reestablish equilibrium, I allow the dog to sit on my lap and I go ahead and I take a nap. So I have established a new equilibrium with the dog on my lap. I guess it's not perfect because it's not clear which way the reaction went, but you're at equilibrium. Something changes. How do you respond? How does the reaction respond? And so this is sort of an introductory slide. It says, stresses that alter the composition of an equilibrium mixture are going to be changes in concentrations, of reactants or products for aqueous species, changes in pressure or volume for gases, and it'll turn out that a change in volume also changes the pressure. So really these are all just changes in pressure, but we will change the volume and figure out how it affects the pressure for gases. And then changes in temperature, and I think it's not just changes in temperature. We'll also sometimes say add heat or subtract heat. I don't quite say we'd say subtract heat. Maybe we would say remove heat. And these are for exothermic or endothermic reactions. So there's lots of ways we can stress or change a reaction to get to a new equilibrium. And if your question is why would we want to do this, let's say the reaction ends at an equilibrium that doesn't make as much products as we would like. Maybe we want to cause the reaction to make more products. All right. So let's start with changes in concentration. And the stress would be added reactant or product, and then it is relieved by the reaction shifting in the direction that consumes the added substance. So here's what I'm going to say. Here's my analogy. So a reaction at equilibrium is on a balanced seesaw or teeter-totter. A reaction at equilibrium is on a balanced seesaw. Also called a teeter-totter. I'm not not sure how to spell teeter-totter all of a sudden. But anyway, so the reaction is balanced, and it is a delicate balance. And so if we add reactant, we are going to be, let's say we add A by increasing concentration of A. And so the concentration of A is now larger. That means that this side will be heavier. And so our picture is that our teeter-totter is imbalanced. And so in order to get to reestablish equilibrium, the reaction must shift right by making more products. Making more products also takes away some of the reactants. That's what doing the reaction does. Making more products and reacting away some reactants. Okay, and so you would just add more A. Not only would it, when it shifts right, it would make both C and D, but it would also, when it does the reaction in the forward direction, it would take away some A and B. So if we were at equilibrium, we had some B, we add more A, we would get rid of some of each of them. Now, likewise, if we add product, the seesaw is tipped heavily towards the product side. The reaction has to shift left by doing the reverse reaction, by taking some products, or let's say this, by making reactants and reacting away products. And again, we have three different ways at least of saying this. So up here, so making more products and reacting away some reactants. Shift right, that's another way of saying it, and do the forward reaction. And down here, we would say, do the reverse reaction. Okay, so that's how it changes in concentration. You can think of it in terms of a seesaw. You can also say, whatever you add, the reaction takes it away. Whatever you add, the reaction takes it away. It's another way of saying it in Chatelier's principle. All right, so that's changes in concentration. And the removed reactant or product is relieved by the reaction shifting in the direction. So now we're going to be removing things. So here's our reaction at equilibrium. And it is balanced. Then we remove reactant. So let's remove, that's how many colors can I get here? So let's remove B. Then our seesaw is lighter on the reactant side, and the reaction shifts. So if it took some away, it makes more, shifts left. And if you remove product, so let's now remove D. The product side is lighter, reaction shifts right. to make more products and take away some reactants and get back to a balanced seesaw. Okay, because a balanced seesaw is equilibrium. Now, how do you remove a substance from a reaction? Let's say that you are at equilibrium for, I had an example here. That's what I thought. Sodium chloride solid dissolving into sodium ions plus chloride ions. At equilibrium. And so how do you remove a substance from a reaction? How we're going to remove it is we're going to add silver nitrate. So the silver nitrate then, so the silver ion reacts with the chloride ion to make AgCl solid, thereby or therefore decreasing the concentration of chloride. And since it's concentration of chloride that shows up in the equilibrium constant expression, that is taking it away. And so really, how do you remove a substance from a reaction? So oftentimes you do an additional reaction. And we'll see this too. Now, how does LeChatelier's principle relate to QC versus KC? So the first thing is, it is exactly the same thing. So it is exactly the same. Meaning that QC versus KC tells you which way a reaction shifts to get to equilibrium, and LeChatelier's principle also tells you which way a reaction shifts to get to equilibrium. So they're exactly the same. So LeChatelier's principle tends to uses no numbers, while QC versus KC uses some numbers, so uses numbers. So if you ever get stuck, you can do either or of these. They are complementary techniques. And so as a reminder, we have a reaction. The reaction's at equilibrium, and so KC equals QC. And for this reaction, both of them, if the reaction is at equilibrium, would be products raised to coefficients at equilibrium. And so, so this is at equilibrium. We increase the concentration of A. That's if we increase the concentration of A, so that's going to make QC will be less than KC. So reaction turns reactants into products. And so, again, LeChatelier's principle would say the same thing. If we increase concentration of A, then, so here, QC and then LeChat. So we would have AA plus BB goes to CC plus DD. Increase concentration of reactants. Reaction shifts right. So they're exactly the same, and we didn't use any numbers there, but if we said increased concentration of A from 0.1 to 0.2 molarity, we could have done numbers there. Okay.